Usha ma'am, now you can proceed.
Yes, ma'am. Okay. Today's topic is power converter interfaces for electric vehicle. I extend my warm welcome to today's speaker, Dr. M. Prabhakaran sir, Professor, VIT, Chennai. It's my privilege to introduce sir to the participants. He has completed his BE from University of Madras in the year 1998. He obtained his ME degree with specialization in power electronics and drives from Bharidasan University in the year 2000. During the year 2012, he completed his PhD from Anna University in the area of resonant DC-DC converters. He has about 20 years of teaching experience at UG and PG level. He received the Outstanding Teacher Award for the year 2009. He was involved as a co-principal investigator and received seed fund worth rupees 3.4 lakhs. He has delivered about 30 keynote addresses and technical talks at various seminars, conferences, and workshops. He has published about 35 papers in various international journals and conferences. He is a reviewer for various international journals like IEEE Transactions on Industrial Electronics, IET Power Electronics, Renewable and Sustainable Energy Reviews, International Transactions on Electrical Engineering System, etc. His area of interest include DC-DC converters, topologies for DC microgrids, and power converter for renewable energy applications. At present, he is working as professor in the School of Electrical Engineering at VIT Chennai. Welcome, sir. Now I hand over the session to you, sir.
Good evening to all the participants. Thank you so much, ma'am, for the introduction. And thanks to the organizers for inviting me and giving me an opportunity to share my thoughts on power converter interfaces for EVs. Actually, I have been working on power converters for quite some time, maybe around a decade or so. But all those power converters were designed for a DC microgrid or a renewable energy application. Of course, my PhD thesis was on resonant converter for automotive application. But then the other converters that I have been engaged with, that I have fabricated, tested, experimented, they are all meant for renewable energy application. In recent times, that is in the past 6 months, maybe 9 months or so, I have been involved with consultancy work from Ashok Leyland. Two of my colleagues, in fact, four of my colleagues, they are part of a consultancy work, and I happen to be one more member, that is the fifth person, where it is especially on EV. Ashok Leyland, they are actually developing a bus. They have an electric bus on their own, but whatever power converter they have, that is being imported, and it is just a brick. Nothing is seen inside. So Ashok Leyland actually wanted to develop their own power converter. So that is the consultancy project, overall consultancy project that I have been involved in for the past 9 months or so. It is based on that background only that I accepted to deliver this address. Fine. So on that note, I'll start sharing my screen, and then I'll pass on to my presentation. My screen should now be visible. Am I right?
Yes, sir.
Yes, sir.
Okay. All right. So we are now, yeah, it's evening time, but then I'm actually delighted to see so many participants. They are still joining, more than 70 of them. I'm happy that people are eager to, I would presume, listen to the addresses being given by various eminent people. Fine. All right. Now, the topic of today, of course, is on power converter interfaces. And I'll be covering these aspects. A lot of background information is necessary because only very few information is available, at least from my perspective, because I have started only 9 months ago to work on this. And that will be my first topic. And whatever commercially commercial electric vehicles are available, what are their specifications? What are their actual ratings, at least from the electrical engineering perspective, which means the voltage level, power level, and the battery capacity. Not much detail is available about the voltage level, but the battery capacity level and then the charging time that is required, those details are available. So that will be my second topic. And then I'll take up some standards. I'll stick on to Indian standards alone, automotive industry standard, AIS. So there are two parts in that. So I'll just give a glimpse of, again, I'll focus only on the electrical terms, glimpse of the standards that one has to adopt, and what are actually the challenges being faced by not particularly power converter interfaces, but then the EV scenario as a whole, and what would be the challenges that power converter designers would be confronted with. So that will be my next topic, and finally I'll summarize, and I'll just speak about the outlook. Where are we heading to? That would be my concluding remark. Fine. Now I have used a few references, not actually papers. They are from, in fact, whatever other than this slide, whatever slides where I have used the material, that is from standard, the automotive industry standard for an example, and the data sheets from several commercially available electric vehicle manufacturers. So other than that, this is the only paper which I had, only journal paper. I should be very specific. Only journal paper which I had referred. It's again an open source journal paper only. So this is how my talk is going to proceed. Right. Now I will actually replace, not replace, sorry. I will actually show this picture again, show this schematic once more, so that where we are heading to, what are the challenges, what are the types of power converters that are required, those details I'll be dealing with later on. Fine. Now, the schematic or the electric power train of an EV is going to be this, and whatever electrical part is involved, majority of the electrical parts are indicated in this. Now, the voltage levels and the power levels, actually both, of course, need to be mentioned so that one gets an idea of what is the power level, what is the ampere, what is the voltage level that we are looking at, what is available with us from the battery, what is given to us, and then how are we going to meet the voltage requirements. Where is the power converter coming into picture? These are the questions that will definitely be answered just by looking at this picture. Fine. Now, first and foremost thing is going to be the glimpse. The moment you look at it pertaining to this topic, I'll just highlight the power converters alone. So we have one DC to DC power converter, another, and then we have a low voltage DC to DC power converter here. Inverter is again another one. We have an onboard charger also, that again involves a power electronic switch. These are all inside the vehicle. Outside the vehicle, we have one more power converter, which is actually the fast charging converter. So these are all the power converter interfaces that one has to keep in mind. That's point number one. Point number two, the voltage levels that we are looking at. Actually, if you can observe, you will have a grid, and then the grid is being the source for the onboard charger. We will look into these details a little while from now. And then from the charger, it goes to the propulsion battery. If it's a fast charging application, again, it's going to be in DC form. Again, it goes to the propulsion battery. From the propulsion battery, we have another bidirectional DC-DC converter followed by the HVDC bus. Okay. And then we have another auxiliary battery as well. Fine. Now, this HVDC bus is going to be 400 volts. This is the main bus that main electric rail, you can understand that way, because EV bus is another term. This bus is the voltage bus that I'm referring to. Whereas the other bus is going to be of low voltage, that is mainly used to supply the auxiliary loads. They haven't marked over here, but this LV refers to low voltage DC-DC converter, where the low voltage, I will write it here, low voltage DC bus. This is mainly for supplying the auxiliary loads, LV bus. So this is going to be at 24 volts. Sometimes they use 12 volts also, but 12 volts is at a very that has developed. It has come up to 24 levels. This is mainly used for auxiliary loads. Yeah, that is why they call it as auxiliary battery. Right? First and foremost thing is the voltage level that we are looking at. Fine. And the next one would be, what is the power level that is going to be involved, or what is the power level that we are looking at? Now the power level is going to be, if you take 24 volts, probably here the maximum power level is going to be somewhere close to 3 kilowatts. Not exactly. These are just approximate numbers. Approximately 2.2 kilowatts, 2.4 kilowatt. That's the maximum power rating of the power converter that is involved. Whereas 400 volt DC bus, this is going to supply the main motor. You can observe here. So from the HV-DC bus or the main DC bus, you have an inverter, and then this inverter supplies power to the main traction motor. Okay, electric motor actually. There are various types that are being used. Three-phase PMS, a permanent magnet synchronous motor, is what is being used in a large number of electric vehicles, except Tesla, which uses three-phase induction motor. Again, the voltage bus level is 400 volts even in Tesla. Now, people are looking at increasing this 400 volts to 800 volts. That's a different story. This I will tell in when I deal with Outlook. Fine. Now, for the power level, getting back to the power level is going to be dependent on the drive. Whatever electric motor is going to be used, so that electric motor capacity, that actually tells us the that determines the power level of the HVDC bus. Of course, slightly overrated, because when the motor is loaded, quite obviously voltage will dip and then it will draw more current to meet the load requirement. Therefore, the power level is going to be somewhat more. So to know the power level, we have to take up we have to look into some electric vehicles that are commercially available, and then depending on that, this bus power level has to be determined and we can understand. Fine. So the first and foremost thing that I wanted to communicate, which is the voltage and power level that we are looking at. Now, to start with this electric motor, I'll stick on with four-wheelers or cars. So in cars, it ranges somewhere around 35 to 40 kilowatts. 40. I'm talking about the battery capacity. 40 kWh. Kilowatt hour is the battery capacity that is involved. This roughly gives you an idea of the drive motor capacity. I'm reserving my numbers for the later slides. When I deal with the specifications, definitely I have got four EVs, they have got the specifications. So you will get to know about the exact number of the power level. I know that this is the energy capacity of the battery, but just giving you an idea. I just wanted to give you an idea of what is the power level that we are looking at. Somewhere around, it should be somewhere about kilowatt range. That is enough for the time being. Definitely more than tens or twelves of kilowatt, tens or 20 kilowatt. Fine. Okay. Now, what is the functionality? What is the function of various power converters? What do these arrow marks represent? Quite obviously, you will be knowing that double-sided arrow mark indicates power flows in both directions, whereas you will never see single-dimensional arrows. Actually, there are one-dimensional power converters or power converters which carry current power only in one direction. That is mainly used for the auxiliary loads. Now, the purpose of this auxiliary battery is going to be some sort of a redundancy, mainly to reduce the load on the propulsion battery so that the range of the vehicle is increased. Number one. Number two, if at all the entire propulsion battery is going to be drained out for a few kilometers, if the vehicle has to run, then power can be transferred from the auxiliary battery. So some sort of a backup. It is not an exact backup. Everybody would understand that. Still, very few, some sort of a reserve, like we use in internal combustion engines. We tell reserve capacity of the fuel. Something like that. They use it for auxiliary battery, but the main objective is to reduce the load on the propulsion battery due to the auxiliary loads like power steering motor is an auxiliary load, headlight, music system, air conditioner. In fact, These are all coupled, connected only to the auxiliary battery, not the main propulsion battery. So this is the structure of the electric vehicle, especially car, which I have taken in this example, in this slide. Bus also, it is exactly similar. Electric bus also, it is similar. Only thing is, people are looking at moving to 800 volt level, voltage, high voltage level. Otherwise, the concept is going to be exactly similar. Fine. Now, on that note, I'll move on to the next slide, which is going to be, this is of course, previous slide we saw inside. This is outside. Given the voltage level, power level, energy capacity of the battery, what should be the charging levels that one should look at, and what are the types of vehicles? E-vehicles. Of course, two-wheelers are there, three-wheelers, auto rickshaws, and nowadays we can see the municipal cleaning vehicles. They are actually electric vehicles. Again, four-wheelers, electric car comes under four-wheelers, electric buses and electric trucks. In fact, e-buses, there is a policy by the government of Tamil Nadu, and there has been a study undertaken by the Bengaluru Municipal Corporation, Transport Corporation, to replace all the vehicles that they are using now by e-buses. So they in 2020 they were having a fleet of 2,500 buses. They wanted to increase that to 6,500 by 2030. So that actually is a very good potential for electric bus. And then they have done a detailed study. I will show that study also, the report also, and followed by e-trucks. Okay. Now, what are the charging levels? If you take a two-wheeler, three-wheeler, four-wheeler, quite obviously their power level is going to be different. That's well known to us. Now, based on that, what are the charging levels? What are the power levels, power ratings of the power converters that we are looking at? That's my intention behind projecting this slide. First one is going to be level 1 charging, where voltage is going to be 240 volts. AC only. This is of course AC. And then the power level is going to be less than 3.5 kilowatt. This is type 1 charging or level 1 charging. This is fit enough for all the two-wheeler, three-wheeler and four-wheeler, all the types of electric vehicles. This comes under type 1 AC charger. I'll show the photograph a little while from now. In the next slide actually. Then there is another DC charging is there, which is level 1 DC charging, where the voltage level as specified by the government of India, it's going to be more than 48 volt. But what is the highest level, they haven't told. If we want, we have to look into the standard EAS, automotive industry standard, and then we have to check what is the DC voltage level. There they have clearly given maximum level that is for level 3 DC charging, that's 1000 volts. But for level 1 DC, they haven't specified. So level 1 DC, it's going to be up to 15 kilowatt, again applicable for all the three segments. And then level 2 is again going to be for AC. This has a voltage of 380 volt to 400 volt AC bus. Here it is going to be less than 22 kilowatt. Quite obviously, this is for if you take four-wheelers, then this comes under quick charging. We have a 7.2 kilowatt quick charging AC charging that again I will project. So there the power rating is going to be less than 22 kilowatt, which is type 2 or level 2 charging. The socket type is also given over here. And then comes level 3 AC charging, again quick charging, which runs up to, this is not 4.3. Of course, the website says 4.3. It must be 43. Should be a typo error because up to 22 kilowatt comes under level 2. So this must be 43, not 4. Again, the vehicle is only four-wheeler. Therefore, quite obviously, this is 43 kilowatt. Typo error. I didn't bother to change. I just kept it like that because it's taken from the website. And then finally, the most interesting one or the excellent one is going to be the DC charging, which is very, very useful, where the charging time is going to be drastically reduced. It takes only DC or even AC, even level 3 quick charging comes under, you increase the power level, then under 1 hour time, 50 to 57 minutes, one can get somewhere around 80% of the total charge. 20% of SOC to 80% of SOC happens in 57 minutes maximum. So 1 hour, you can take 1 hour. Fine. So that's these are again voltage and power levels that are being used in the all the three types of vehicles. Now, how are the charging pins going to look like? Because some of you might have seen this. If it's boring, kindly bear with me, because for me it was a new thing. Uh, Only when I prepared or started, maybe 9 months back, when I started getting into this, I came across the charging types of, types of sockets involved in EV charging, and which regions. Globally, it's not uniform, it's not standardized. That's another issue. If you take Outlook, there it can be dealt with in detail. Uh, Now, these are the types of sockets which are being used. You can, first and foremost thing is, over the globe, it varies. It's not standard actually. Right? Though North America and Japan, they seem to use same type, whereas DC, they are different. In AC type, they are same, but DC, they are different. DC, it's completely different actually. And you look at Tesla, you take Tesla, except European markets, they are standardized. Right? Now, China is totally different. Both in AC and DC, they are totally different. They don't fall under any of the other continents, European Union or Japan or US or other market. The best part comes in the last column, which is India. India is actually trying to adapt all the types of sockets which are used globally. You will get an idea of once you look at the picture. Now, this is our own standard, our own Bharat. Previous slide I had indicated the type Bharat type 1, Bharat 001. That's the socket. I'll go back to the previous slide for recollection sort. So this type Bharat AC 001. So this socket is this. Okay, type 1. And so this follows the European Union and the rest of the market. Same thing is true with the DC sockets as well. So India is actually trying to standardize all the three options. Either it could be GBT or SHAdeMO, or it could be CCS1, combined charging system. So this is what India is adopting. Right? Again, this comes under I think a frame where faster adoption, revolution of adopting e-mobility. So it comes under that policy. So government has got very good policies on EV adoption. Fine. So these are the sockets. These are the types that are available. Fine. Now, how do they look like? This is of course I have taken only Bharat AC 001. Type 1 AC charging only I have shown, because the commercially available vehicles, again I have restricted myself to Indian vehicles, few Indian vehicles alone. They use only type 1 AC charging, CCS2, that is for quick charging. Fine. So this is how the charging station, the plug point or the socket in the charging station is going to look like. And this is another version where one can actually take out and just like we use in a petrol pump station or diesel pump station, we can just take that gun, charging gun. It's called as a charging gun, CG. So you can take that CG and then insert it in our vehicle, and we can get it charged. Depending on, this is of course type 1. So it is going to take around 6 to 8 hours. So it's not quick charging, it is normal slow charging only. Understand that way. Fine. And these are the vehicles that use type 1 charging, AC charging, type 1 AC charging. MG ZS EV, Tata Nexon, and then the Hyundai Kona Electric. Mahindra e-Verito is actually stopped, discontinued. Instead, Mahindra has introduced XUV 422 EV version. So that uses type 1 AC charging. Similarly, Tata Tigor Ziptron, and then Tata Tiago EV, that also uses the same thing. And of course, the most not what is this? They are called as luxury sedans, luxury vehicles. They also use type 1 AC chargers. Fine. So far I have now covered the rails. How does inside the vehicle? What are the voltages, power levels, where the power converter is going to be involved, and then I took up what is the voltage level, power level for various types of charging levels, and then the sockets that are involved. This is what I have covered so far. Now, let us look at the next interesting aspect, which is going to be the commercially available EVs. What is the power level? What is their battery capacity? What is their range? So on and so forth. Now, first and foremost, I've taken Tata Nexon because this is the most successful commercial EV to date, at least in India. Okay, so this comes with, I have focused only on the electrical part. The mechanical part, like tire comfort, convenience, whether we have an airbag, etc. Those things I haven't focused on in this presentation. Now, if we take Tata Nexon, this is of course EV maxed out. Maxed out meaning it has got a higher range, it has got a higher power motor, and it has got additional comfort and convenience features also. So I have taken that. So the motor is again PMSM, permanent magnet synchronous AC motor. Okay. Power rating in PS is 143 PS. Again, giving a torque of 250 Newton. This is maxed out, 250 Newton meters. Drive modes, they have got various options. Based on the drive mode, the power that is being consumed by the drive motor, that is going to be different. Based on that power consumption, range is going to be different. That's the understanding. That is what one should understand. And then the battery pack is 40.5 kilowatt hour lithium ion battery pack. In fact, all the manufacturers, they come with they are using lithium ion batteries for the main battery pack. Right? And then it is a liquid cooled arrangement. In fact, just now I was talking to my son who said that the charger is going to draw a lot of power. It gets heated up, therefore that is going to be liquid cooled one, where there will be a small tube which runs in parallel to the converter, the charging gun and the converter. That's what he was suggesting. In fact, these details I should thank him, acknowledge him. He was the one who had taken up and given me these details. Fine. And then the emission is not required for our case. Now, what is the charging time? CCS stands for combined conductive system or combined charging system. CCSL, right? Combined charging system, actually. Combined charging system. And then it has got a cable. So these are the two options. Now, this 3.3 kilowatt is the normal charger. Normal, slow charging. I don't want to put it as slow. Anyway, just to distinguish, I'll put it as slow. Quite obviously, this is the fast charger, right? In AC socket. And just look at the time, you will understand the difference. So if it's in 7.2 kilowatt AC fast charger, it takes 6.5 hours. Whereas in normal socket, it takes 15 hours. So 2 times reduction. Now compare that with the 50 kilowatt DC fast charger. Just 50 minutes, 1 hour. Fine. So 1 hour itself is actually, this is really good when you compare 6.5 hours and 1 hour. That's a drastic reduction. But 1 hour to charge a vehicle, where do you wait? How do you wait? And how do you spend your time? In fact, right now, there are, I myself, I have seen quite a few number of vehicles lined up in, let's say, when I travel from Chennai towards Trichy highway, there is an A to B, Adayar Ananda Bhavan near Dindivanam, where there is a charging station. I've seen 2 EVs, 2 Tata Nexon EVs charging over there, and then people go have their breakfast, lunch, etc. So maybe they can spend around 30 minutes. By that time, it would have charged, the vehicle would have charged to around 40-50%. So that gives them the required range. So that some sort of a range anxiety. There is a term range anxiety. I'm sure you would have come across that in the earlier sessions. So that range anxiety would be slightly reduced because their vehicle has got 40% charge. Therefore, they can safely reach home. So if it's a fast charger, if it's a 50 kilowatt DC fast charger, otherwise half an hour time is not going to make much difference. the SOC will not rise that much, maybe 20%. That's all. Beyond that, it's not possible. Fine. So this is about Nexon EV Max. Therefore, from the power converter perspective, this is of course outside the EV. Please understand that this is outside the EV, not within the EV. But then you have to look at EV from a very broader perspective. Don't be so narrow, don't be so focused. Focus only on the EV. No, that you can do later on. But power converter person will have opportunities both inside the EV to work inside the EV and outside the EV. Outside the EV for charging, chargers to develop chargers. Inside the EV for that power converter, actual interfacing power flow concepts, etc. Now, next comes XUV400. This is again a very recently introduced EV. I heard 1 minute. Again, you look at the motor, electric motor power. It takes around it operates at around 110 kilowatt, and then the battery pack is 34.5 kilowatt for this version, XUV400 EC. The other version is slightly again slightly zoomed out version or slightly enhanced version. EL comes with the 39.4 kWh battery pack. Again, same standard CCS2 charger type. Again, it takes around 50 minutes, I believe, 50 minutes to charge to full capacity in DC fast charging. The other one is Kona Electric from Hyundai. This was introduced in 2022. This again has got 39, yeah, here 39.2 kilowatt hour will be the battery capacity. Again, same lithium ion battery. Look at this, 6 hours and 57 minutes fast charging, DC charging. DC fast charging around 1 hour time. Right? Fine. So motor type again PMSM. 1 minute, I'll go to XUV400. They haven't given the motor type, I remember. Yeah, first one. PMSM. Fine. So Nexon PMSM, XUV PMSM, Kona Electric PMSM. Right. I have one more EV, which is the MGES. Yeah, MGZS EV. Sorry, MGZS EV. So this again uses a 3-phase PMSM, 142 PS at 3500 RPM. Then this again has a battery capacity of 44.5 kilowatt, same 7 hour to 50 minute charging time. This also uses Type 2 CCS, right? Charger connector. The reason why I project this and the reason why I projected the socket types, you should be able to correlate how the socket will look like, will appear. That is the reason why I projected that type earlier. Right? So type 2 will have a round type and then there will be 5 or 6 holes. So that's how type 2 will look like. Okay. Now, by now you should have come to an understanding about what is the power level, what is the energy capacity of the battery, what is the time that would be required to charge the vehicle to, let's say, 70%, 80% of the full SOC. And under fast charging, DC fast charging, the standard voltage will be around 1000 volts. Power level is going to be 50 kilowatt. So the converter should be able to deal with that much amount of power. Right? At that voltage level, 1000 volts, 50 kilowatt is what one is looking at. Right? So, and quite obviously, we don't have a 1000 volt source, DC source. So we may definitely have to, if we have 3-phase AC, again rectify that, boost it up to 1000 volts at 50 kilowatt, use that. Or if we use, let's say, solar panel based battery charger for 2-wheelers, not 4-wheelers. For 2-wheelers, power level will be less. That's why I'm suggesting 2-wheelers. So it's going to be 3 kilowatt or 4 kilowatt maximum. Voltage level again 240 volts. It's going to be fast charging for 2-wheelers and 3-wheelers, of course. So that you can look at where the power converter does the role of charging. the battery. Fine. Now, how do we standardize this? What is the standard? Uh, what are the standards being used for the charging system as such? So AIS, automotive. This is again strictly for India, Indian standard. This is abbreviated as AIS 138. There are two parts. Both specify the electric vehicle conductive DC charging. So that's their norm. So conductive DC charging, where they have very clearly defined the reason why I put this left hand side is what is a charger, what is called as a class 1 charger, class 2 charger, etc. What is called as on-board, off-board, dedicated off-board. Dedicated means it's only for that particular EV. It's not compatible with other EV. That's the meaning of dedicated on-board charger. And what is slow charging, what is fast charging, that also they have defined. Fine. This is important to us. Now, slow charging means it is going to charge with single phase with 15 ampere socket. And the socket type is going to be whatever we saw, Bharat AC 001, something similar to our air conditioner. Not exactly, not exactly. Might be same, might look same, but check the standard number. Only then you can be absolutely sure that both are exactly same. Okay? It looks like that. That's what I'm suggesting. And then the fast charging is going to be from a three-phase socket. Three-phase socket at 63 amperes. Okay? So this you can relate to AC fast charging. You can relate to Tata Nexon charger, 7.2 kilowatt AC fast charging charger, and slow charging. You can again same Nexon 3.3 kilowatt. So that you can correlate. Right? And from the battery capacity, Tata Nexon was about 40.5 kilowatt hour, and the single phase 15 ampere at 3.3 kilowatt. From there you can compute the time. That will be about 6 hours, 6.5 hours. Similarly, AC fast charging, you can compute the time. That should be about 1 hour. We got around 57 minutes was the specifications. So this is how we compute the time that is required. What is the role of the power converter over there? Because it plays a very, very important role in meeting the voltage requirement of the battery and the socket that is going to be available. Fine. Now, what is this mode? What does the standard tell us? Now, the standard tells us that the current cannot exceed 15 ampere, which means who should do this job? The power converter should ensure this. Fine. That is why I have put this standard also. We should know before we dive into power converter and then deal with waveforms. We should know this. Of course, today I won't show any waveforms. Maybe first time in so many years that I'm not projecting any hardware results. Anyway, I'll give you other content. Fine. Now, EVSE represents electric vehicle supply equipment. That's what EVSE refers to, electric vehicle supply equipment. EV will be clear, supply equipment. Now, they have, again, you can refer to the standard, easily downloadable for more information. So if it's going to be a slow charger without an onboard charger, then we need a power converter interface. This is the reason why I had put this. So if it is without onboard charger, if it's with the onboard charger, the power converter part will be inside the vehicle. Inside the vehicle, as we saw in slide 2. Plot. Fine. So this is about the slow charging mode, the specification. Standard says it cannot exceed 15 ampere. Nominal voltage also is set, plus or minus 10%, which means from single phase is given here. So in India, if you take 240 volts, so 240 volts plus or minus 10%, 24 volts. So that is the voltage level. Current level, it should not be beyond 15 ampere. The power converter, intermediate power converter, whether it is off board or on board, should ensure this. Now, what about fast charging mode? It will be really interesting actually. We have 415 volt plus or minus 10% norm, then 63 ampere. Okay, this comes with an onboard option only. So there will be a power converter inside, and that power converter should operate at 63 amperes, work from 415 volts, and then do the necessary power conversion stage. Quite obviously, AC to DC first, and then that DC to battery pack DC. It has to feed in the power to charge the battery pack with current limit being set at 63 amperes. Voltage level after rectification, I'm talking about the rectification. After that, that depends on the battery pack that manufacturers use. That voltage level they haven't specified. There is one level which is 360 volt is one. People combine lot of cells, lot of lithium ion cells in series in parallel. That is how they get a battery pack, and then they end up with 400 volts straight away, or they end up with 360 volts. Right? There is no boost converter inside the from the battery to the DC rail. They are not using a boost converter. They are not using. At least in Ashok Leyland, they are not using. Be very clear, I'll repeat. From the battery pack to the 400 volt DC level, they are not using a boost converter. Right? Which means the battery pack itself is going to be somewhere around 350 to 400 volts. Or if it's going to be at 300 volts, there will be a intermediate buck boost converter simply to just boost it. But that's not actually present. The battery pack will be slightly higher. They take it up to 450 volts, and then from there they bring it to 400 to 350. That's what they are doing actually. Fine. Then this is another standard. This is also in part 1. So far we have seen AC slow charging standard, AC fast charging standard. Now DC fast charging, it's at 1000 volts. I will point out that to you. Yeah. Okay. So, and 50 kilowatt. 50 kilowatt is the power level. Voltage is going to be up to 500 volts to 1000 volts. All right. This is of course page number. Ignore this. Now, whenever the voltage is going to be more than 1000 volts, what is the norm? Okay, the norm says, or the standard says, disconnect the DC power source within 5 seconds. Right? And what is the difference between two levels, two buses? It's going to be less than 110%. Okay, between DC plus and PE is actually power earth or power conductor. That is this point, ground. We can understand that. This is power earth. Therefore, you can observe that when you measure the potential between the EV and the take a common ground, plus DC to that cannot be more than 110%. Similarly, minus DC to that, it cannot be more than 110. It cannot be more than 110% of the voltage sent by EV. Okay, that's again stipulation. That's the norm. Time is going to be just 5 seconds. So it is the role of the power converter to ensure this, right? Because the voltage level is high, 1000 volts, 500 volts to 1000 volts. Power level is also extremely high, 50 kilowatt. And the difference in voltage cannot be more than, cannot exceed 110% of the DC output voltage. Time is just 5 seconds. Therefore, this has to be correlated to the challenge. So if there is a fault, if there is an overshoot, then the power converter should act immediately. The dynamic response should be excellent, or that's what one would prefer. Okay? So these are the requirements, or these are the challenges that one is looking at from the power converter perspective. Fine. So this is about DC quick charging, DC fast charging. Okay, now I get back to the powertrain again. As I said earlier, I will show the project the same diagram so that now my intention will be to tell you what is the actual power converter that is being used and what are the challenges that we are looking at. One challenge that we came across right now is the dynamic response perspective. Now, the types of DC to DC converter that people are using, industry is using, they are actually using a classical buck converter, and then they are using bridge type. It is full bridge in one system, half bridge in other system. Bridge type DC to DC converter. Right? They are focusing only on this. They are using and the standard three-phase inverter. This is again a classical three-phase bridge, which is now available in the form of a brick, IPM, intelligent power modules. They come along with protection. Fine. Industries they haven't yet adopted novel topologies where there are many switches, where there are again control aspect. See, the battery charging, they are again following the same classical constant voltage, constant voltage, constant current. That's all. These are the types that they are using: constant voltage, constant current, trickle charging, of course. Trickle charging, this occurs after the battery reaches 90 percentage, which is being set by them, 95 percentage, and then it reaches till it reaches 100 percentage. That's actually trickle charging. Fine. So these are the converters. They use a buck converter, bridge type DC to DC converter, and then they charge the battery using constant voltage, constant current mechanism, constant voltage or constant current. And for fast charging, that is of course off-board. So the main requirement is this is again connected to the AC bus. Therefore, in both cases, in this and in this, here, the power factor of the overall system, that is going to be extremely important. Supply side power factor, especially in this, because power level is extremely higher. Therefore, the moment, let's assume there are 3 vehicles and all the 3 vehicles need quick charging. So roughly it's going to be 150 kilowatt being consumed from the AC mains, from this mains. Therefore, these are non-linear devices, non-linear converters. Hence, the power factor is likely to fall down drastically. But then there are solutions. They come with power factor correction, where they again use SEPIC converters for power factor conversion. SEPIC converter is used. Flyback converter is again another topology which they use inside. Inside means here, either here. Okay, they're not. I am referring to the industries. Industries, unless and until we prove the reliability of the power converters, industries will not adopt them quite easily. They want the converters to be run for hours and hours, months, years together, prove the reliability, prove their costworthiness, efficiency, and then they are ready to adopt. That's again another challenge. Fine. This is from the converter perspective. From the drive perspective, from the motor perspective, I'm sure you would have come across, but still the most prominent one seems to be PMSM. That's what all the manufacturers they are using. And there are various control strategies where vector controlled drive is there, and then bidirectional mechanism is going to be there, which is already given over here. So the regenerative braking mechanism, for that some sort of a control mechanism needs to be there, and the power converter should also facilitate that. But then not much is required from the drive perspective. From the motor, the motor alone, not much. Otherwise, control topologies and other things, yes. Right now, being faculty members, I am sure I can share this information with you. Yes, we do have various journal papers saying this, especially on control topology, machine learning based, etc. Only then we get a paper, etc. But industries, they don't adopt. Remember, industries, they don't accept unless and until we prove them experimentally. Simulation wise, it will work. Simulation, it's our own algorithm, it will work. But experimentally at that power level, with a very good dynamic response of less than 5 seconds, for instance, for DC fast charging, you have to have a power converter which clearly demonstrates that capability to meet that standard. Okay? So if there are any research scholars, if there are any other faculty members who are interested in working this, then you keep the standard in mind. In fact, you can download the standard, you read that standard, keep that standard in mind. Your work has to be aligned with that standard. It has to be in that direction. Don't take any random values, any random numbers, and then start doing, it won't be useful. You might get a paper, but it might not be really useful to the community as such. It might be useful to you personally, but individually, but to the entire fraternity, it may not be useful. Fine. Now, let me list out the challenges one by one. First and foremost thing is the reliability of the power converter. Right? So, if there are more switches, how does the reliability affect the performance when there are more number of, let's say, switches or semiconductor devices? It could be diodes as well. When there are many numbers, when we use them in plenty, then the likelihood or chances of their failure also increases. Failure rate. It's not actually failure rate, it's chance to fail, chances of failing. This also increases. Therefore, industries are quite wary of power converters which use lot of switches. Fine. Instead, there is a way out. If all the switches are brought out and in the form of a brick, you take one single brick, and then you let's take the example of a intelligent power module IPM. It's just a brick, one single brick, but inside there can be 2 switches, 4 switches, or 6 switches. It could be a half bridge, or a full bridge, or a 3-phase bridge, full bridge. So such things industries accept because there the failure rate is minimal. The brick doesn't fail too often. Whereas if you have discrete semiconductor devices here and there, in distributed over the circuit, over a larger area, then reliability is a question mark. Okay. Then quite obviously the space that is available in the vehicle is less. So the power converter has to be compact. Definitely weight. If we come out with a very heavy inductance, magnetic element inductance or a transformer, high frequency transformer, then again that is going to play a role on the range of the vehicle. In fact, the auxiliary battery I was talking about in the beginning, the auxiliary battery, if it was not there, the range comes down by 10%. So the auxiliary loads, they are disconnected. Quite deliberately, they are actually decoupled from the main propulsion battery and then they are connected to the auxiliary battery so that the range improves by 10%. Similarly, the weight of the power converter definitely has an impact on the range of the vehicle. Definitely efficiency so that the battery lifetime, again that extends to range indirectly. This supports range indirectly. So efficiency, people are looking at above 97% efficiency. Fine. And this dynamic response is what I was highlighting when I told the DC charging standard. Within 5 seconds, the shutdown has to happen if over voltage occurs. Not only that, when the load on the system, when the load on the motor actually, load on the EV increases, again the power has to flow through the power converter part. Therefore, the power converter should respond very quickly. Right? This is where the control algorithm becomes important. Not to say, I'm not saying have a very complex algorithm so that nobody understands. No, that's not what I'm suggesting. Again, industries use only PID controllers. Very finely tuned PID controllers is what they depend on, not our machine learning, AI, complex AI, etc. No, they haven't adopted that because, again, proven fact. Okay. All right. So that's another challenge which we may have to deal with. Then control strategies, about which I was talking about a little while from now. And then this again I highlighted, especially for the slow and fast charging, you have to have a very good power factor, very close to unity. 0.95, 0.98 is what is needed because the power level is extremely high. Again, in India, has the government of India has put a standard for this, especially for charging stations, which is going to be on the utility, on the electric, the onus, the responsibility is on the electric vehicle utility to install charging stations which operate at good power factor. They have told 0.9, 0.95, etc. More than 0.9 is what they have specified. So coming out with a power converter which operates at 50 kilowatt, gives 1000-volt DC, takes supply from the AC and operates at 0.9, good challenge. Okay. And it has to be compact also, cost effective, compact, etc. These are again other challenges. Fine. Now, for the what is this short-term demand? I'm referring to this as the sudden pickup that might be needed. How does the power converter respond to this? It is connected to dynamic response. Similarly, one needs to have a quick charging mechanism. Again, how does the power converter, how does the overall system involving power converters, how do they respond? These are all challenges that one needs to look into, especially the failure rate. This is connected with the failure rate. Suddenly, if you draw more current, then if you have many semiconductor devices, likelihood of failure increases. Or if you use a huge magnetic element, it could be a high frequency transformer or an inductor. When we draw higher current, then the response becomes sluggish. Fine. So these are challenges that one may have to keep in mind. Now, this is again a very, very interesting challenge which is expected to come up in the next few years or so. Because if you can recollect, the battery capacity was around 35 to 40 kilowatt hour of one EV, one car. Let's imagine an apartment where there are 10 EVs. So the battery capacity is going to be 400 kilowatt hour. So it is like a mini grid, pico grid, micro grid, etc. You can actually supply power to your nearby flat or nearby single bedroom apartment, etc. Or you can use it for your own use. Right? That is going to be vehicle to grid sort of a system. And who takes care, who keeps a tab on what is the amount of power that is being injected to the grid, what is the power that we consume for charging our EVs. Let's take Sundays. Out of 10 vehicles, 8 may remain not in use, 8 may not be used. So that battery of all those 8 vehicles, that will be around 200 kilowatt hour, more than that. So we can use that. We can use that power, we can use that energy, and then we can feed the nearby locality. This concept is going to come up in a big way. How does the power system, existing power system network, how is it going to adopt? So there has to be a lot of policies in a lot of aspects. There has to be a trading policy or a pricing mechanism must be there, and there has to be a scheduling mechanism, because it's not reliable again. You can promise them that I will send you 50 kilowatt hour. I have a battery of 35 kilowatt hour. Therefore, I will be able to send you, let's say, 10 units. Fine, from 10 a.m. to, let's say, 2 p.m. But then suddenly you get a work and then you drive your car. Who takes care of that, etc. So these are good interactions. This is where policies need to be framed. Not only that. See, EV battery, yes, we are charging, we are delivering it to the grid. Who takes care? Who should keep a tab on the grid protocols? Are we going to meet the grid protocols? Therefore, somebody should have a watch, should have a tab, should have an eye on these things. Okay, so that's again another interesting interaction, which is going to be quite challenging technically. Right? The concept is there, but then it has not been demonstrated. People were trying to demonstrate in Delhi, but a lot of things, as I said, pricing mechanism, scheduling mechanism, contracts, what sort of a contracts you put with the users. These things have to be worked out, sorted out. Fine. Now, coming to the outlook and summary. So, I started off by telling you that the 400 volt DC bus is what is being used in the existing vehicles. People are thinking about using 800 volts mainly because it takes half the amount of time to charge. Because when 400 volt DC bus, if it takes, let's say, 1 hour, 800 volt DC bus, same capacity, it will take only 30 minutes. Okay. But then there is another school of thought which says, okay, then 800 takes 30 minutes, then will you go to 1600 volt, etc.? It doesn't make sense. True. But I think Hummer, they are moving. I have that. I will show you once my presentation ends. Hummer, they are going to move towards 800 volt. There is a talk among the e-bus, e-truck manufacturers to talk about 800 volt because they are heavy vehicles. They demand more power. So that's again another outlook which you can look forward to. This goes without saying, actually. There is a huge potential for EV vehicles across all segments, meaning two-wheeler, three-wheeler, four-wheelers. Nowadays, as people, we have now understood the benefits of EV, not green. It's not green, it's actually cheap, that's all. The ownership cost is very much reduced. That's what I would say. Rather than saying I love environment, therefore green contribution. Those things are all maybe for advertisement sake or publicity's sake. Personally for me, I'm not generalizing. But as a customer, if I want to buy a scooter, two-wheeler, electric scooter, then my first and foremost thing that I will look at is cost, ownership cost. That's all. And nowadays it's becoming competitive. EVs are becoming competitive. They give us uh, an edge, slight edge over the petrol two-wheelers, autos and cars. That is why Tata Nexon is famous. Fine. And then this again, we should accept the proactive government policies, be it center, state, they are fighting with one another politically, but that's a different ball game. However, both the state government, central government, in fact, all the state governments, they are proactive. They are thinking on proper lines. Their thought process is fine. Implementation aspect is taking a long time. That happens whenever new concept, whenever new theme actually emerges, it happens. But then they are thinking on the right lines. So that needs to be complemented. This is again a very good thing from the years to come, from the outlook perspective. This I have told, and vehicle to grid also I have elaborated. One more thing, vehicle to vehicle. Suppose there are two electric vehicles side by side traveling on the highway. There is a concept which says that they can communicate with each other. In fact, I again heard from my son that in MG Hector, there is an option which says that you press a button and then it can communicate, it can send an SOS, save our soul, send a message, something like that. Later, it can be extended to communicate between two vehicles, vehicle to vehicle, and it could be vehicle to anything as well. That is why they have put it as vehicle to X. So from one vehicle, you can charge the other vehicle. Vehicle, you can give it to grid, or from one vehicle, you can give it to another, let's say, car to bike. That's also so. Therefore, that is called as V2X. These concepts are going to emerge in the years to come. So, on that note, of course, I have not drawn any power converter circuit. That's again new for me. But my intention was to give you a very broad perspective because the power converters that are used in the vehicle, they're well-known, well-established power converters which are available in textbooks. Therefore, I didn't take any effort, any pain to draw any circuit and then explain the design of an inductor, etc., as I would normally do in other presentations. Fine. On that note, I'll wind up. If you have any questions, I'll be glad to answer. Thank you so much for your patient listening.
Yeah, participants, if you have any doubts, you can ask or you can post it in chat box.
Sir, Sarojini Harikrishnan has asked, could you please suggest any particular standards for choosing power converter voltage for traction motor design?
Traction motor for an electric vehicle or traction, are you meaning the trains?
So for electric vehicles, sir, I'm asking.
For electric vehicle, you need a standard for choosing the power converter.
Yeah, sir.
Okay, simple. It again the power converter should meet depending on where you use. Actually, it's for your traction purpose, right? Traction means the drive motor, right?
Yes, sir. Electric car.
Drive motor, of course, today I don't have that with me. Okay, you can do one thing. You can look into this automotive industry standard. There are some other standards also. Of course, 1 and 2, they deal only with The charging standard, I have collected only that. The
Okay,
drive
sir.
motor, there will be a standard. I haven't come across that so far, but there should be a standard.
Sure, sir.
Yeah.
Thank you, sir.
Yeah, right now I haven't come across, therefore I am unable to answer your question clearly.
Shall I refer this AA, sir?
Same AAS you can refer.
Okay, sir.
This
Thank
is
you,
of
sir.
course Indian standard. Indian standard. You can refer European standard or IAC standards also.
So next,
Okay, sir.
Fine.
Thank you so
Santakumaran
much.
has asked, wireless charging system is possible for e-vehicle.
It is possible. Fast charging may not be possible at 50 kilowatt because the efficiency is very low. You would know that the efficiency is going to be 30-40%. Herculean task to obtain such a high efficiency, but slow charging might be possible. Normal charging or slow charging might be possible, but I haven't so far in my preparation or over the 9-month duration. I haven't seen a practical wireless charging infrastructure. It is there conceptually, but technically whether somebody has implemented, at least I haven't come across. Photographs are there, but those photographs I don't rely on them unless and until I see a data sheet. I won't trust. So yes, it's possible. If you ask me, is it possible? Possible, but whether it is there, I'm skeptical.
Participants, any other queries?
Good evening, sir.
Good evening.
This is Arpude Mary from VIT Select, sir, research scholar. Sir,
How are you?
yeah, I'm good, sir. Good, sir. Sir, actually, very long ago, I have a doubt regarding the industry perspective. So that's what in none of the paper they have, even the website also, they didn't have mentioned anything about the what kind of converter they are used, what kind of controller they are. Only thing is they are putting the battery capacity and even the nominal voltage as well as the amps and all. They didn't mention anything. The only things what I have understood is so far the charging harness depends upon the ampere. It's based on the ampere hour. Okay, while increasing the ampere, automatically this will lead to the increase in temperature of the battery, right, sir? So automatically the battery life battery life gets decreased. So what is your opinion on this, sir?
I mean, I'm not an expert on that, but so far your statements are absolutely right. I can only tell that.
Okay,
Yes, it
sir.
does have an effect on the life of the battery. Definitely, yes. But there has to be a study whether definitely a study would have been carried out how fast charging affects the lifetime of a battery. But I haven't again gone through that study. Therefore, I'm not able to have. I'm not able to comment on that whether it's right or wrong. My opinion, I don't have an opinion on that actually.
Okay, sir. Okay, sir. And also in many papers they have mentioned so many new converter, like a novel converter. This will be used for so many EV application like that and all. But in real time, whether this will work or not, we don't know anything about that. So today I got some clarity on this, sir. Very much thank you to you actually. Very thank you, sir. Very thank you. Thank
Pleasure.
you for your presentation. It's very good, sir. Thank you, sir.
So next question is, what are recent or novel power converters, DC-DC converters suitable for e-vehicle?
Recent, I think the previous question or previous remark is the answer to this question. Novel converters, yes, anybody can come out with a novel converter if the reliability is proven to the industry in a clear-cut way. Then any novel converter can be accepted. Fine. How does one prove the reliability? There are two ways. Number one, which industries prefer, is you build that converter, bring it in the form of a brick, bring it in the form of a block, as the way it has to be used, run it for 24/7 for months, years together. That's point number one. That's the first and best way to prove the reliability. Next way is analytical way. There is a very rigorous mathematical analysis. It is called reliability analysis. where the failure rate of each and every component in the power converter, they fix a particular probability. Let's say we have a classical buck converter. It has got an inductor, it has got a switch, it has got a diode and a capacitor. So they fix a probability of failure for each of these 4 devices. And then they carry out reliability analysis study. Then they end up with saying, okay, this converter is this much percent reliable, etc. So these are the 2 ways by which you can prove the reliability. After you prove the reliability, any converter is going to be, you yourself will know whether it's reliable or not. How do you enhance the reliability, etc. You will get clarity once you do the reliability analysis. So again, it is an open-ended answer only. It can be an open-ended answer only, mainly because the reliability of a buck converter is proven. Classical converters, they are proven. Novel converters, they are not proven. They are available only in journal literatures. Fine.
So next question is, could you refer any standard books for converter design on EV applications?
Not so specific, because again, converter is not so specific. It is again generic, no? Classical buck converter, boost converter, buck boost converter, etc. You can refer to one textbook on JANES and so many other authors. So they have a separate chapter on power converter for EVs, but that again is going to be the classical converters only. So don't be surprised or don't expect something new, novel topology. It will again be same classical buck boost, etc.
Participants, any other queries?
Sir, one more question, sir. Sir, in your architecture, you are mentioned about the switches like IGBT you have mentioned, but in most of the bidirectional or else converter which is used for EV application, they in journal paper they have used only the MOSFET. Why IGBT? Why not MOSFET, sir? Switches.
Actually, IGBTs are more reliable. They are more rugged compared to MOSFETs. MOSFETs are like kids, infant babies. The failure rate is extremely high. The moment electrostatic discharge happens to the gate terminal, they fail. So comparatively, IGBTs are much more reliable. They are robust. Therefore, industries and journal papers as well, they prefer IGBTs compared to MOSFETs. Number 1. Number 2, switching frequency is going to be only 20 kilohertz, not more than that, because EMI issues will pop up when we go beyond 20 kilohertz. Therefore, IGBTs will serve the purpose well. Considering these 2 reasons, IGBTs are used.
Okay, sir. Thank you, sir.
I hope that answered your question.
Yes, sir. Yes, sir.
So next one is lithium material was found in Kashmir. Is there any possibilities to a reduction of battery cost?
Not able to answer that. If it is available, yes, it should generally reduce in cost. But then again, I haven't read that news, therefore I'm not able to comment on that.
HOD sir?
Yeah, ma'am.
Shall I conclude?
If there is no doubt from the participant, then we can conclude, ma'am.
Yeah, okay, sir. Thank you, sir, for the wonderful session. It was in-depth knowledge about power converters, interfaces for electric vehicles. Today's session was very interactive and lively session. You gave more insight about charges, specifications, and charging standards and challenges. Thanks a lot for detailed explanations, sir. I extend my sincere gratitude to our Dean, Dr. V. Jamuna ma'am, for joining with us. And I thank our HOD, Dr. S.VINOD sir, for providing this platform. I extend my thanks to all the faculty members of EEE department. At last, I thank all the participants. Thank you. Participants, you can fill the feedback form and you can leave the meet.
Sir, thank you for accepting, sir, and delivering a wonderful lecture, sir. Thank you, sir.
Thank you so much, Dr. Vinod, Dr. Arul, and other faculty members. Thank you so much for the participants.
Thank you, sir.
You stayed here in respect of 7.
Yeah, thank you, sir.
Thank you, sir.
Ma'am, we can wait for a few minutes and then we can leave, ma'am.
Okay, sir.
Is there any requirement, ma'am? We have to there, or if we close, the entire meeting will close, I think so. Okay, ma'am. I will leave, ma'am. Thank you.
Okay, sir. Thank you.